The tangent ratio. There's a total of 3 ratios that we're going to be looking at. The other 2 are called the sine and the cosine. However, we'll be looking at those separate from this video. And all of this is going to be about the study of trigonometry. Trigonometry is the study of the relationship between angles and side lengths and triangles. Up until this point, we had never really worked on angle measurements and side lengths together. Okay, so when we're thinking about triangles, we've used the 180 rule a lot, right? That the angles need to add up to 180. Okay, and then separately, we may have done things like Pythagorean Theorem. And that would be if you had a right triangle, you could take 2 side lengths and then figure out what the third side would be. However, we have never worked those types of problems together. We haven't taken angle measurements and used those to figure out what the side lengths would be, or vice versa. We hadn't taken side lengths and used those to figure out what the angle measurements are. And that's what trigonometry is about. It's about being able to take the angles and find side lengths, or take side lengths and find the angle measurements. And all of it is going to begin with the concept of proportionality. All right, so what I have here is a picture of 2 right triangles. And these 2 right triangles, I'll go ahead and add these little boxes in here. All right, now these 2 right triangles are not completely different than each other. So I'm going to take a protractor and show you that the measurement of this angle here looks like it comes out to be about 36, maybe 37. Let me make sure I got that set correct. Yeah, about 36 or 37. So if I go over here, you're going to notice that I get the same thing. I get about 37 degrees right there. Okay, so the intention here is to show you that these 2 right triangles aren't completely different. They both have a right angle. They also both have a 37-degree angle, which would mean that the third angles would also be congruent, and that would be 53 degrees. But these would be 53. All right, so based off of those angle measurements, we know one thing for sure. These 2 triangles are similar. All right, in addition to that though, if the triangles are similar, the sides are going to be proportional. Okay, these will be proportional. Let me go ahead and take some measurements just so you can see here. The base of this is going to be 4 centimeters. The base here is going to be 6. Okay, so as far as like a ratio, to go from here to there, that would be a 1.5 scale factor. Okay, the ratio would be 4 to 6 or 6 to 4, but you could use a scale factor that could take you from the small one to the big one of 1.5. All right, and the same thing should hold true for the verticals here. We've got 3, okay, and if I multiply 3 by 1.5, that would give me 4.5, which is what I get here. I get 4.5. All right, so if the triangles are similar based off of their angle measurements, we can conclude that the side lengths will be proportional. So all this is going to lead to a really neat observation about right triangles. Okay, so I might not have emphasized the point yet here, but what I am looking at are right triangles. Okay, and the observation that we're going to make here is that the leg length ratios, so that'd be like the 3 and the 4, 4.5 and 6, the leg length ratios will correspond to particular acute angle measures. Okay, so if I have a right triangle with a 37-degree angle, which also means you have a 53, okay, but if I have those angle measurements, what I'm going to get is a 3 to 4 ratio. I'm going to get a 3 to 4 ratio. Okay, now I've got another triangle which is larger than the other one, but it has the same angle measurements, 37 degrees and 53 degrees. Well, the leg length ratio here, 4.5 to 6, is going to be the same thing that we get here. Now, of course, 3/4, you can evaluate that as 0.75. Okay, and if I evaluate this one, you're going to get the same thing. I'll go ahead and show you that one just because it has a decimal in there. If I take 4.5 divided by 6, I also get 0.75. All right, so our observation tells us that in a right triangle, if you have the same angle measurements here, the ratios of the leg lengths are going to be identical to each other. All right, so I have this one last statement right here that I actually couldn't fit on the screen at the moment. Okay, but it says, for example, okay, referring here to the leg length ratios corresponding to acute angle measures, For example, a triangle with a leg length ratio of 3 to 4, that will have acute angle measures of 37 degrees and 53 degrees. These things are tied together. Okay, now your triangles can be bigger or smaller, but that 4.5 compared to 6 would reduce back down to a 3 to 4 ratio. You could actually change it in that. So any triangle, any right triangle that has acute angle measurements of 37, 53, that will have leg length ratios of 3 to 4. And that information will be consistent. So what we can do here is start to organize this information. We could literally start creating a list of like all the acute angle measurements that we could have within a right triangle and the ratio that they would correspond to. Okay, and the way we're going to do that is using what is called the tangent ratio. Okay, the tangent ratio will be the ratio of the leg length opposite of an angle to the leg length adjacent to it. Okay, so let me draw a picture to go along with this. Okay, and again, all of this is using right triangles, which is important that we remember right now, that this is going to be based off of right triangles. Okay, so here's a picture of a right triangle. We're going to choose an acute angle to focus on and call that angle theta. We're going to call it theta. That would be the symbol for theta. Okay, so let's suppose this is the angle we're thinking of, which would mean maybe we're thinking about the 37 but not the 53. Okay, now with respect to that angle, this side right here, which is across the figure, you can call that the opposite side. Okay, and then with respect to theta, you can call this side here the adjacent. Okay, so adjacent means next to and in contact with. So this side would be the adjacent, that would be the opposite, it is not in contact with theta. Now technically, the third side here is adjacent to it. It fits that definition. However, we're going to be referring to that one as the hypotenuse because it's across from the right angle. Just for the sake of confusion, the hypotenuse is the hypotenuse. The leg length will be the one that we call the adjacent. So the tangent of theta, the tangent of this angle, will always be equal to the opposite side length divided by the adjacent side length there. So what is tangent? You've probably seen it as a button on a calculator. Okay, next to that is sine and cosine, which we'll talk about on a different day. So tangent, you can sort of think of it as almost a like database of information. That if I type the tangent button, then follow it up with an angle measurement like 37 degrees and evaluate it, which means just press enter, what I'm going to get back is a response as a ratio. And you're going to notice that that one is about 0.75. So this is the actual ratio that would compare the opposite side to the adjacent side for a 37-degree angle. All right, so most triangles, you're not going to have whole value angle measurements like 37 degrees match up to whole value side lengths like 3 and 4. Okay, that's not likely to happen. Okay, so what probably happened here is when I was measuring with a protractor, I went ahead and rounded it at 37, but it would actually be just 37 and like a teeny bit more, or maybe just slightly less than 37. All right, so if anything that I talked about beforehand felt confusing, rest assured here, the calculations are not difficult. These are really easy problems to actually do. All right, what we have here is a picture of a right triangle with an angle measurement of 35 degrees that had been identified. What we're asked to do here is figure out the length of this side right here, which would be opposite of that, okay, it'd be opposite of that angle, and we are given the side length here, which is adjacent to the 35 degrees. Okay, so my tangent ratio says this. The tangent of an angle, I'm calling it theta here, the tangent of theta is equal to the opposite side length divided by the adjacent, which I'll just abbreviate here, opposite and adjacent. Okay, things that we have. Theta, we have that, it's the 35 degrees. Okay, so I can write tangent 35 is equal to, we don't know the opposite side, so I'm going to put a B up top. We do have the adjacent side, so place a 6 there. And the goal is to solve for B. Okay, so don't pay much attention to this right now. What we have over here is B divided by 6. So if I were to multiply by 6, multiply that side by 6, these would cancel, and I'd get B by itself. Now to balance things, I'll just make sure that I multiply this side by 6 as well. And this is something that we can evaluate in a calculator. The tangent of 35 is just going to give you back the ratio that we should get. That's what it's going to give you, and then when we multiply it by 6, it will figure out what the b value is. All right, now when you do these calculations, your calculator is going to have two different settings. It's going to have degrees. It is also going to have what are called radians. Okay, so at the top here it says radians now. If you use radians for these problems, it's not going to work. So you want to make sure that you are in degrees. Okay, so I'll go back and reset that. All right, and all I need to do here is multiply 6 by the tangent of 35. So I can just type in 6. I actually don't even need to type multiply. Just type in tangent 35, press enter, and that's it. 4.2. We'll have to round these answers, but that looks pretty good, 4.2. Now you can do things in pieces as well. You can take the tangent of 35, go ahead and figure out what that is, okay, and then multiply that by 6, which will give you the same answer. So it just depends on what type of calculator you have. But overall, the calculations are fairly easy. It's mostly going to come down to using that setup. All right, example 2, the problem is not going to really be that much different than what we just looked at. We do have a right triangle. We have an angle that's been identified as 38 degrees, okay, and then we have the side opposite of it. What we're looking for is the adjacent. So that will be the difference in the problem, that we're looking for the adjacent side this time. All right, but we can still start with this. All right, our theta is going to be the 38 degrees. So we have tangent 38 is equal to, we do have the opposite side this time. So you're going to be able to put the 4 on top. What we don't have is the adjacent side, so we'll put a C on the bottom for that. All right, so you can solve it in 2 parts, which is what I'm going to demonstrate first. But when I'm done with that, I'm going to show you a shortcut that I use. All right, so in the 2 parts, what you actually have to do is multiply both sides by C. Okay, because you need to get that out of that denominator position. All right, so that'll give us C times tangent 38 is equal to 4. All right, and then to get C by itself, you divide by the tangent of 38. This will cancel. That'll cancel out, which will give you C by itself. So ultimately, C is going to be 4 divided by the tangent of 38. Okay, and that will evaluate, let's see, we got 4 divided by tangent 38. That will give you, so we'll write over here, C is equal to, let's do 5.12, since it seems really close to that. All right, and that'll be the value C. All right, now as a shortcut, because whenever you have one of these problems and you're looking for the denominator, it would always be the same 2 steps. You would always multiply your variable over, it shows up on that side, and then divide your tangent. You'd have to divide out. So as a shortcut, if you have this, okay, and it doesn't just apply to trig. This would be any situation where you have something is equal to a number over your variable. If you have that situation when your variable is down here, what you can actually do is just switch these 2 around. So if I switch them, I'm going to get C is equal to 4 over tangent 38. I refer to that as cool trick number 4. Saves you a bit of time here. Ultimately, gets you to this place, and it works every single time. At any point, if you have a variable in the denominator, just switch that with the other side of the equation, and you're good to go.
Wait, what?